Hi, thanks for joining me. Today I'm going to have a play around with a problem which kind of is inspired by this guy here. If you plug into your calculator 10 times 9 times 8 times 7, and then you plug into your calculator 7 times 6 times 5 times 4 times 3 times 2 times 1, you will get the same number each time. And this is quite cool because it kind of looks like a sequence 10, 9, 8, 7, and then you kind of repeat the 7 again, 6, 5, 4, 3, 2, 1. And in fact, we can write this left-hand side here as just 10 factorial over 6 factorial, and his right-hand side here as just 7 factorial. Now we want to know, does this happen more than once? Can we find some other numbers where we can essentially have x factorial over y factorial equals y plus 1 factorial? So here, in this case, x is 10, y is 6. So you've got 10 factorial over 6 factorial equals 6 plus 1, which is 7 factorial. We want to know, are there other pairs x and y which sort of have this cool property here? So are there x and y such that x factorial over y factorial equals y plus 1 factorial? Okay, so if you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to jump straight into a solution. Okay, before we get stuck into a solution, I just want to say that this solution kind of uses a few number theory tricks which you don't see all too often, especially in sort of these number theory problems, so hopefully you'll be exposed to some cool new ideas if you've not seen them before. Anyway, let's get stuck in. What we're going to do is just rearrange this equation here, so we get x factorial equals y factorial times y plus 1 factorial, but of course y plus 1 factorial is just y plus 1 times y factorial, so this guy here is just y factorial all squared times y plus 1, like so. Cool, we have this equation here, and if we just have a stare at this, we see on the right hand side we've got something squared times something. Now if we just consider the prime decomposition of the right hand side, most of the primes will be raised to even powers. And the reason for that is because any prime coming from y factorial, when we square it, it's now going to have an even exponent. So most of the so if we consider the prime decomposition of the whole right hand side, most of the primes will be to even powers. And any primes that have an odd power must come from this y plus 1 here. So if we knew what y was and we considered the prime decomposition of it, any primes which are raised to odd powers must be factors of y plus 1. Okay, and of course, since the left hand side equals the right hand side, we have this identity this idea that most of the prime factors of x factorial will be to even powers, but there may be a handful which are to odd powers, and that will kind of correspond to factors of y plus 1. Now what we're going to do is suppose, oopsie daisy, we have a prime p, so p a prime, but it's between x over 2 and x. So we have a prime which is between x over 2 and x, so strictly greater than x over 2 and strictly less than x. Well, clearly p is going to be a factor of x factorial because p is a positive integer less than x. So when you consider x factorial, it's going to be x times x minus 1, and eventually you'll get to p and all the numbers below it as well. So x factorial will be a multiple of p. But because p is bigger than x over 2, x factorial will only be divisible by p once. It's not divisible by p squared or p cubed or anything like that. And that's because if you look at all the other terms, you're not going to be able to get a p out of them. So if you just want to see an example for that to help make a bit more sense, if you consider 5 is less than 7 is less than 10, so this is the case where x is 10 and p is 7. If you look at 10 factorial, it's going to be 10 times 9 times 8 times 7 times 6 times 5 and so on. So it's going to have a 7 in the product, so it's divisible by 7, but none of the other terms are going to give you a multiple of 7 because 7 is bigger than 5, so you can't get up to 14 in time to kind of get another 7 as a factor. So hopefully that makes sense. So if p is a prime between x over 2 and x, then p will be divisible by x factorial will be divisible by p, but it won't be divisible by p squared or p cubed. So we know that if we look at the prime decomposition of x factorial, it will have a p in it, and it will be raised to the power of 1, and 1 is an odd number. So that means that p must come from y plus 1 by the argument we just had. So p then is a factor of y plus 1. But we can't have that p is a factor of y factorial as well, because if p was a factor of y factorial, then that means that when we kind of compute this right hand side, we're going to have p to some positive even number times p times 1, p to the power of 1, sorry. So we'll have p to the 2k here So this is if p divides y factorial. So then when we look at y factorial squared, we'll have p to the 2k and then times a p here. So we have p to the 2k plus 1, and that equals p to the something. So if we just kind of look at the powers of p, we'll have p to the 2k plus 1 equals p, just p alone, which means that k must be 0. So that means that p can't actually divide y factorial. But if p can't divide y factorial, but p is a positive integer, that must mean that p is at least y plus 1. Because if p was a positive integer less than y plus 1, then it would be in the product y times y minus 1 times y minus 2 and so on. So that means that p is also at least y plus 1. But because p must divide y plus 1, we have that p is less than or equal to y plus 1. And just combining these two pieces of information, we have that p equals y plus 1. Okay, so what we've done is we've shown that if p is a prime which is bigger than x over 2 and less than x, then p must be equal to y plus 1. But what this also tells us is if there are two primes between x over 2 and x, then we're going to have some issues. Because we can't have, so if there were p1 and p2, say, so if we change this to now p1, p2, then using this argument that we've just had with p1 and p2, we'd get that p1 equals y plus 1, but we'd also get that p2 equals y plus 1, and then we get p1 equals p2, which is not possible because one must be bigger than the other if they're different. So that tells us that we only really need to consider when there's only one prime between x over 2 and x. Because if there are more than one prime, we're not going to be able to satisfy this. We're going to have sort of a contradiction. So we only need to consider the cases where there's only one prime between x over 2 and x. And for that, we're going to use Bertrand's postulate. Let me clear up the whiteboard and I'll explain what that is, and then we'll continue. Okay, so we're going to be using Bertrand's postulate. Now, there are in fact a lot of different versions of this postulate, but this is the one we're going to be using for this video. I'm not going to be proving it, I'm just going to be stating it and then using it to solve our problem. This one says that for n at least 12, we can find a prime p such that p is between n and 4/3 n. So it's at least n, but it's at most 4/3 n. Now I'm going to use this to show that if x is large enough, then there can't be any solutions. And the way we're going to do that is we're going to show that if x is big enough, then I can find two primes between x over 2 and x, and by the previous argument, that means that there can't be any solutions to our problem. Okay, so what we're going to do is firstly consider x over 2, and notice that this is strictly less than x over 2 plus 1. Now, supposing x is big enough, then we know that by Bertrand's postulate we can find some prime p1 between x over 2 plus 1 and 4/3 x over 2 plus 1, like so. But then we know this number here is strictly less than 4/3, oopsie daisy, x over 2 plus 1 plus 1. But then we can apply Bertrand's postulate again on this guy here. So if we let this guy here now equal n, then there's some prime p2, which I'm going to have to go to the next line for, which is between that and 4/3 of that guy there. So 4/3 x over 2 plus 1 like so. But this guy here, I'm just going to call d for now, just so I don't run out of room. This guy here is strictly less than d plus 1. And now, if we just notice that if we make x big enough, if we just look at this guy here, this has, the coefficient of x here is 4/3 times 4/3 times a half. If 4/3 times 4/3 is 16 over 9, which is strictly less than 2. So the coefficient of x here is some number just a bit less than 1. So that means it's growing smaller than x. So that means for some very, sort of if I make x large enough, this guy here is certainly going to be less than x. Now I'll leave it to you as sort of an exercise to work out what x that is. I think x around 35 should do the trick, and then you can prove that by induction that this inequality here holds. And of course, if x is bigger than 35, then that means that x over 2 is bigger than or equal to 12. So we can in fact apply Bertrand's postulate. But what this says is for x large enough, we can find p1, or there exists p1 and p2 between x2 and x. And you'll notice I was very sort of technical because I had to make sure that I introduced this guy here, that x over 2 plus 1 is less than or equal to p1. So then that means that p1 is certainly strictly greater than x over 2, sorry. and then I had to add on these ones here just to be extra careful, because it could be that the prime equals n or equals 4/3 n, so you've just got to account for that by being super careful. But for x large enough, there are no solutions. So in fact, we only need to check x for small cases of x, so x beneath 35. I can't remember what the bound is on x, but if you want, you can do that as an exercise. But I've written down the solutions here. The only solutions are xy then equals 1, 0, 2, 1, and 10, 6. So you just check all the values of x from 1 to 35 and see which ones work and which ones don't, and you'll see that you'll only be able to get these guys here as your solution. I hope you have enjoyed this number theory video. It's the first time I've ever used Bertrand's postulate to solve a number theory problem on the channel, and it's a really fun tool and something to have in your toolkit if you've not seen before. I do encourage you to look up the other versions of Bertrand's postulate as well, because you never know when you're going to need to use them in a number theory problem. Anyway, thank you for watching. I'll catch you in the next one. Have a great day.